All right, so if oxygen is absent, what we have is pyruvate getting converted to lactate in order to recycle the NAD plus back into the cytoplasm. That way we don't run out. That way, theoretically, we could continue the process of anaerobic glycolysis until lactic acid builds up to such a point where the process is shut down. All right? This isn't sustainable. If you were relying only on this source of energy for metabolism or for your ATP, you'd find that you could only last a minute, maybe 2 at the most, before the lactic acid built up to such a point in your system where you would be forced to stop exercising. However, if oxygen is present, we have a much different situation going on, and that's what we want to look at next. So what happens if oxygen is present? If oxygen is present in the system, what happens is that we see that the pyruvate that were created during glycolysis are transported into mitochondria. And this is why mitochondria are required for this step, as well as oxygen. It's because this is going to happen almost right away. All right? Those pyruvate are going to get converted into something called acetyl-CoA. Okay? Pyruvate get converted into something called acetyl-CoA. That CoA stands for coenzyme A. All right? And then we're going to see that we kind of continue on from there. So let's go ahead and draw this out. All right? What we have here is we have pyruvate and coenzyme A combining with one another. And this happens inside the mitochondria. So pyruvate plus coenzyme A are converted into acetyl-CoA. We want to keep track of our carbons just a little bit. So remind ourselves here that pyruvate is a 3-carbon molecule. All right? Acetyl-CoA, on the other hand, though, is a 2-carbon molecule. So we see something that sort of looks like that. All right? Okay, in this conversion of pyruvate to acetyl-CoA, what's going to be happening? Well, the first thing that we have to do is we have to account for the carbon that we just lost, right? We notice that pyruvate is a 2-carbon molecule, a 3-carbon molecule. Acetyl-CoA is a 2-carbon molecule, so we have to account for the carbon that just disappeared, all right? And we're going to see that what happens is that CO2 is produced, right? You are probably aware that when you exhale, what you're exhaling is you're exhaling carbon dioxide. And part of that carbon dioxide that you exhale is coming from this conversion of pyruvate to acetyl-CoA. Okay? The other thing, though, that we're doing, and again, I said that we're going to be coming back to this over and over and over again, is we are observing another redox reaction. All right, what we have is we have NAD getting converted to NADH. All right, what do you think that we're oxidizing in this process? What is being oxidized and what's being reduced? Well, we're adding an electron to NAD+, so NAD+ is what's being reduced, and we are oxidizing our fuel molecule, and our fuel molecule here is pyruvate, our substrate. So pyruvate is getting oxidized, and NAD+ is getting reduced. All right, and this is what we end up with. We end up with this conversion that we see right here. Okay. Remember that for every glucose molecule, this happens twice. All right, for every glucose molecule, this happens twice. So we end up with 2 acetyl-CoA molecules per glucose. All right, that acetyl-CoA which is this 2-carbon molecule, is then going to enter the citric acid cycle. All right? So it's going to combine with something called oxaloacetate, O-X-A-L-O-A-C-E-T-A-T-E. Oxaloacetate is a 4-carbon molecule. Okay. So we're going to have oxaloacetate and acetyl-CoA combining into something called citrate or citric acid. And again, this is happening in the matrix of the mitochondria. 2, 3, 4, 5, and 6. So we're ending up with a 4-carbon molecule, a 2-carbon molecule. We add those together, we get a 6-carbon molecule, citrate or citric acid. Okay? And this cycle that we're going to be entering here in just a couple of minutes, or a couple of seconds, I guess, is called the citric acid cycle. All right? The citric acid cycle is named because of the first step, which is citric acid or citrate. It's often sometimes called the Krebs cycle. It was named for its discoverer, Hans Krebs. And we also will sometimes call it the tricarboxylic acid cycle. You're going to see it named a number of different things, but I believe that the most current and proper name for it is the citric acid cycle. All right. Now, the citric acid cycle is a cycle, meaning that we're going to eventually return to oxaloacetate, right? And I'm not going to make you learn every intermediary of the citric acid cycle. Again, when you take biochemistry or something like that, you are going to be asked to learn the names and the structures of all of the intermediaries, right? So citrate gets converted to isocitrate, that gets converted to alpha-ketoglutarate, so on and so forth. I don't care that you learn those intermediaries. What I do want to do here is I want to look at the details of what's coming out of this. All right. Well, again, let's go ahead and tackle something that hopefully is a little bit obvious first. The first thing that we see happening is we have a 6-carbon molecule getting eventually cycled back to a 4-carbon molecule, meaning that we lose 2 carbons somewhere in the process. And as you might have guessed from our previous discussion about the conversion of pyruvate to acetyl-CoA, we're going to lose those carbons as carbon dioxide. So let's go ahead and pull those CO2s out here as well. CO2, and we have a loss of CO2 right about here as well. I'm putting these in their approximate place on the cycle, but it doesn't really matter. All right? However, the big thing that we've got going here, and the one that you might have guessed based on my theme for the day, is we have a whole series of redox reactions. And that's really what the citric acid cycle is a series of reduction oxidation reactions in which we're producing even more of those high energy electron carriers. So we have NAD plus getting converted to NADH. We have NAD plus getting converted to NADH. We have NAD plus getting converted to NADH. And then we have another high energy electron carrier that we haven't actually mentioned yet, but it's very similar to NAD+. It's called FADH2. I'm sorry, FADH. And when it gets reduced to FADH2. Serves the same purpose, it's just a different molecule. All right. So the bottom line here is that we have a whole bunch of a whole bunch of reduction oxidation reactions that are producing just a whole boatload of these high energy electron carriers that we're going to see here in just a couple of minutes. All right. The other thing that we're producing on this is we're producing an ATP. All right. So an ATP is being produced here as well. Again, this is called substrate level phosphorylation. So we have an ATP being produced as well. All right. So the citric acid cycle takes place in the mitochondrial matrix, and we see that there are just a lot of high energy electron carriers being produced, right? We're taking that fuel molecule, that acetyl-CoA, and we're putting it through a cycle where we're oxidizing it as much as we possibly can, right? We're taking off as many electrons as we can, and we are going to use those electrons in just a couple of minutes to drive ATP synthesis. Remember, for every glucose molecule, this wheel, as it were, is going to turn twice, right? So everything that we see here in terms of the products that are being produced, we're going to have to multiply by 2 when we update our bookkeeping. Why don't we go ahead and update that bookkeeping right now so that we can kind of keep everything straight. We had glycolysis that we added a little bit ago. Let's go ahead and add a couple of more things here, right? So let's go ahead and look at 2-pyruvate being converted to 2-acetyl-CoA. Okay, well, that process didn't use anything, so we can put an X in there. And we saw that we had 2 NADH that were being made and 2 CO2, right? That's what was made in that process. I'm not going to carry the CO2 over because we don't really care about that much, but I am going to carry the 2 NADH over. All right, so there we have that. And then I'm going to go ahead and add a line here for the 2-acetyl-CoA. In the citric acid cycle. Right? The 2-acetyl-CoA in the citric acid cycle. We made 2 ATP. We made 6 NADH. And we made 2 FADH2. Okay? Carry that over. 2 ATP, 6 NADH, 2 FADH2. Oh, and we made, I guess, what was it, 4 CO2, right? Okay, so there's our total kind of bookkeeping for this process so far. So what I want to do is I'm going to kind of put this up just a hair. I'm going to add just one column here, or a row, I guess, to this worksheet. The only way for me to do it is to do this. So what I want to do is I want to draw my line here, and I want to say the total yield for one glucose. Okay, so if we add this up, what we've done is let's take our ATPs first, right? We had 2 here, we had 2 here, so we have 4 ATP. Okay, I had 2 NADH made in the cytoplasm. That's a cytoplasmic. And I had 8 NADH in the mitochondria. There's a difference there we'll talk about in just a couple of minutes. But those cytoplasmic NADH don't often yield as much energy as the mitochondrial NADH do. So I'm just making that differentiation so that we can kind of return to that later if we have a little bit of time. And then we have 2 FADH2. So at the end of this process, at the end of glycolysis and the citric acid cycle, we've produced 4 ATP, okay? But we know that ultimately we're going to get over 30 ATP from this glucose molecule. So we still have a long way to go, right? But most of the energy that was stored in that glucose molecule is now tied up in these high energy electron carriers. So glycolysis as well as the citric acid cycle, the main point of those is that we are just simply producing a whole lot of these high energy electron carriers, right? We're taking electrons off of our substrate molecule and we're transferring those electrons over to these, right? Remember that the removal of electrons is called oxidation, and that's why we call this oxidative metabolism. All right? Okay, so let's go ahead and take a look at what happens next in this process. Let's go ahead and remind ourselves a little bit of mitochondrial anatomy. Right? Mitochondria are just about my favorite organelle. Right? They're these kind of bean-shaped organelles. They are double membrane, meaning that there's an inner membrane and an outer membrane. That inner membrane is folded, and the reason behind those folds is because there are enzymes that we're going to meet in just a moment that are critical for the production of ATP. They're found on that inner membrane, and the more inner membrane there is, the more of those enzymes there are. All right. So the citric acid cycle happened here in the matrix. So the majority of those high energy electron carriers that we produced in the last step are going to be floating around here in the matrix. All right? The ones that were produced in the cytoplasm around the mitochondria are going to be transferred into the matrix. All right? So they're going to be transferred across. So eventually all of those high energy electron carriers that we've produced so far are going to be floating around here in the matrix, and they're going to start to interact with enzymes that we see on the inner membrane of the mitochondria. Right? They're found all along this membrane. So let's go ahead and take a look at a section of that membrane and kind of see what we have here. So what I'm going to do is I'm going to take a section of this membrane and I'm going to blow it up. Right? We're going to take a much closer look at that. So here's my inner membrane of my mitochondria. Right? I'm not going to draw all those phospholipids, but we know that they're there. There's my inner membrane. So out here is the matrix. And in here is what we call that intermembrane space. Okay. And on that inner membrane, what we find is we find a series of enzymes. Okay, we find a series of enzymes. And these enzymes are what we kind of collectively call the electron transport system. All right? They're all very similar to each other. We have these kind of 4 enzymes that are found on the inner membrane. So I'm going to draw these 4 guys. Right? They're embedded on the membrane. You can see that they do span the entire membrane, right? They're found on both sides. Let me draw my last one here. Right? So they have these enzymes that are found on the inner membrane of the mitochondria. Okay? There aren't just 4 of them, right? Remember that there are hundreds or even thousands of all of these enzymes, but there are 4 separate ones that we're sort of looking at. They are part of the electron transport system, right? These enzymes all have names, but they also have generic names as well. They're often just simply called complex 1, complex 2, complex 3, and complex 4. All right? So let's go ahead and look at what the electron transport system does and why it's important. Now, remember that all of those high-energy electron carriers that we've been following are floating around in the cytoplasm. All right? So here we have an NAD, I'm sorry, not in the cytoplasm, in the matrix. All right? Floating around here. So here we have an NADH. And eventually, it's going to come into contact with complex 1 of the electron transport system. All right? When it comes into contact with this enzyme, we're going to see, you guessed it, a redox reaction that occurs. Okay? Now, instead of oxidizing this guy, instead of reducing this guy, we're going to be oxidizing this guy. So NADH is oxidized, an electron is removed, and we end up with NAD+ as a result of that. That electron is transferred to complex 1, so complex 1 is now reduced. All right? See what we did there? Okay. Now, what's going to happen is that this electron is going to be transferred from enzyme to enzyme to enzyme. Okay? So this guy was just reduced. It's now going to be oxidized, and this one is going to be reduced. This one is going to be oxidized, and this is going to be reduced. This one is going to be oxidized, and this one is going to be reduced. So it's a chain reaction that begins when this guy is oxidized. All right? And that electron is passed from enzyme to enzyme to enzyme. What that does is it provides energy. That redox reaction that occurs provides energy for us to pump a proton across the inner membrane of the mitochondria. So every time we see a redox reaction in one of these enzymes, what we do is we take a proton and we pump it across the inner membrane of the mitochondria. When we see that reaction between these enzymes, a proton is pumped. Right? When we see the reaction between these enzymes, a proton is pumped. When we see it between these guys, a proton is going to be pumped across. So when we have hundreds or even thousands of these, what we end up with here in the inner membrane space is we end up with a proton gradient. Those protons are just floating around in the matrix, and as we go through this redox reaction, chain reaction in the electron transport system, those protons are actively pumped into the inner membrane space. So what we end up with is we end up with a lot of protons in this area of the mitochondrion. Okay? And that's because of the redox reactions involving these NADH and FADH molecules that are produced. Okay? FADH2 enters a little bit further down the line, so it ends up not pumping as many protons across, but the reaction is still the same. The idea is still the same. Okay? Now, at the end of the electron transport system, here at this last enzyme, that electron is eventually going to be kicked off of that enzyme, and it's going to get accepted by oxygen. Okay? So it's going to kind of get kicked off. That electron is going to get kicked off, and we're going to see 2H plus 1/2 of oxygen, or an O, getting converted to water as a result of that. All right. So oxygen is going to accept that electron. That's going to allow it to bind with a couple of these guys, and we're going to produce water as a result of that. That water is what we call metabolic water, and you end up producing about 1/2 liter of it a day. But oxygen here is the ultimate electron acceptor, and that's where that electron eventually goes. So if you think about it, if you start with a glucose molecule, a sugar molecule, what's happening is that the electrons that were on that are ultimately getting converted to water. And a lot of that water is what you exhale as water vapor. So it's kind of fun to think about the fact that these electrons are getting swapped around on these different molecules, and the molecules that they get swapped to actually are tangible for us. Okay, so this is what's happening in the electron transport system, right? We have this process occurring, we have a proton gradient that is being produced. So what happens to that proton gradient, right? Well, you have probably learned in just about every single biology class that you've taken that gradients of anything don't really like to exist in biology, right? They typically like to dissipate via diffusion, and that's what's happening with these protons as well, right? We're pumping them all into one space, but naturally what they want to do is they want to diffuse across the membrane back into the matrix. There's another enzyme that we find on the inner membrane of the mitochondria, right? I'm going to extend my little snippet of membrane just a little bit here, right? There's my snippet of membrane that we have, and I'm going to draw this last enzyme on here. This enzyme is a fairly large enzyme. It consists of two main parts. This enzyme is called ATP synthase. Okay, and this enzyme ATP synthase has a passageway that allows for the diffusion of those protons. So these protons that are all building up here in the inner membrane space are going to start to diffuse back into the matrix via ATP synthase. So it's a passageway that allows for that diffusion. All right. However, these two subunits of ATP synthase sit on top of each other, kind of like this. All right? And every time a proton passes through, what happens is they turn on each other, kind of like a ratchet. And every time, or every several times that it ratchets, that provides the energy for us to make ATP. So here we have adenosine diphosphate plus an inorganic phosphate getting converted to ATP, right? So this is how the ATP is made in this process, right? The entire thing that we're looking at here, the combination of the electron transport system and ATP synthase, is what we call oxidative phosphorylation. Right? Oxidative is referring to the transfer of electrons here in the electron transport system, right? Those sequential reduction oxidation reactions. And phosphorylation is referring to what's happening with ATP synthase, where we have the phosphorylation, or the addition of a phosphate to ADP to make ATP. Those two processes have to work together in order for ATP to be made, right? If ATP synthase were not working, this process would not result in the production of ATP. It would just result in the production of a proton gradient. And similarly, if this process were not working, this enzyme would just sit here doing nothing and ATP would not be made. So they have to be together in order to work. Because they have to be together in order to work, we say that those processes are coupled, right? We've coupled the electron transport system with ATP synthase in oxidative phosphorylation.